Hello.
Hello. Hi, everyone.
Hi,
Hi.
Shahin.
Hi, Joseph. Good afternoon. I guess
Hi,
it's
good
afternoon in
afternoon. Hi.
Munich, right?
Thank you
Nice to
for
meet you.
joining. We have also Shangding here, who is the host today. I'm the group organizer. Thank you for accepting to talk here. You already got a notice we're automatically recording this. You can decide later on if you are okay with sharing this or not. We can also disable recording if it's not fine for you. You can just let us know. And you can decide after the talk. We have a channel for safe reinforcement learning that Shangding is maintaining, so maybe you want it published there or not. So is it fine for now to record or not?
Yes, of course. Yeah. Please proceed with the recording.
Okay, great. Thank you. So let's just wait for all the people to join,
Sure.
and then we can start with the meeting. I'll just enable you to be able to share screen, so you'll be co-hosting. Hi everyone, thank you for joining. So we have an invited talk today. Maybe now I give the stage to Shangding so he can introduce the speaker for today, and then we can start with the talk.
Hello, Shahin. Nice to meet you.
Hi, Shanjing.
Yeah, it's my pleasure to invite you to give a talk for us. So I will introduce Shahin. Shahin is a PhD student in computer science at the University of Albert. He previously obtained a master's degree in software engineering and intelligent systems from the University of Albert, Canada, and a bachelor's degree in computer engineering from Confine University. Is right?
Kafkas University.
Yeah. Azerbaijan. Shahin is developing explainable reinforcement learning approaches for autonomous driving in his doctoral research. And he has presented the preliminary findings of his study in AAAI 2022 and was awarded a prize of the presented research article. His current research is funded by the Ministry of Science and Education of the Republic of Azerbaijan, Huawei Technology Calendar, and the Department of Computing Science at the University of Alberta. So, today, Shahin will introduce his talk about the development of explainable reinforcement learning approaches for safe and interpretable autonomous driving. So let's welcome Shahin to feel free to share your screen and start your talk.
Thank you very much, Shanting, for introduction. Sure, I will just start sharing my screen and start talk as well. So can you see my screen now?
Yes.
Okay, awesome. So can we start now?
Yeah.
Okay. Thank you very much for joining today's talk. It's my pleasure to give a talk for you. And I would especially like to thank to Shanting for organizing today's meeting. My name is Shahin Atakshev, and I am a PhD student in computing science at the University of Alberta. And I am a member of Explainable AI Lab at the University of Alberta. In this work, I am working with Dr. Mohammad Salami from Huawei, Canada, and my supervisor is Professor Randy Gobel. The title of today's talk is Development of Explainable Reinforcement Learning Approach for Safe and Interpretable Autonomous Driving, which is my kind of ongoing doctoral research.
So just one comment, we're not seeing the full screen, we're seeing the PowerPoint. Are you sharing in full screen or it's just the...
Oh yeah, actually just... Can you see now or?
Yeah, we can do it like this also, it's fine, but we're seeing everything, the whole window, so it's not full screen mode. I'm not sure. if you're sharing in full screen mode or not. Slideshow?
Maybe.
Yeah, I think this is a little better if it's fine for you. Yeah.
So is it fine now?
Yes.
Yeah, it's fine now. Yeah.
Okay, awesome. Thank you very much. Okay, so this is a brief agenda of my talk. I will give a brief overview of autonomous driving. Then I will show the need for explainability of AI in autonomous driving. Then I will shed some light on reinforcement learning and explainable reinforcement learning for autonomous driving. Furthermore, I will talk about safety benefits of explainable AI in autonomous driving and give information about my ongoing work and sum up the presentation with conclusions. So what's autonomous driving and how decisions are made in autonomous driving? So at the highest level, autonomous driving consists of 4 basic operations, which are perception, localization, planning, and control. So perception is an autonomous car's ability to sense its operational environment using several sensors, such as video cameras. Then localization is a car's ability to understand where it has stood in a specific time state geographically. Then planning means an autonomous car chooses the best route from initial point to final destination. And finally, control means chosen actions are executed properly. So by this way, an autonomous car can perform actions like steering, adjusting speed, and staying in a lane, and keeping a distance. So this is a kind of high-level operations associated with autonomous driving. So currently, there are 6 levels of state-of-the-art autonomous driving, which has been defined by SAE International. These levels change from level 0 till level 5. So in level 0, there is no driving automation, which are kind of old cars. So we can say cars in 20th century. Then in level 1, there is a driving assistance where adaptive cruise control is applied. In level 2, the cars have advanced driving assistance systems. Then in level 3, cars have an ability for obstacle detection. And finally, in more highly automated driving systems in level 4, there is a near full automation in a geofenced area, such as Alphabet's Waymo claims that they are in already level 4. And finally, the highest level is full driving automation, where there is no any human supervision required and everything is fully automated. And still, there has not been kind of a car which has reached level 5, yet it seems very ambitious to reach to this level. But still, there are a lot of research projects that try to achieve level 5. So why do we need explainability of AI in autonomous driving? So based on my research, I have identified that there are at least 3 main reasons that necessitate explainability of AI in autonomous driving. First reason is psychological perspective, such that traffic accidents and the current safety concerns with the presence of autonomous vehicles are big issue. So if you look at this example, for example, Tesla sedan hit a parked police vehicle in Laguna Beach, California in 2018. So kind of traffic accidents and existing safety concerns and issues is kind of bringing psychological perspective, psychological perspectives for the need of explainability of AI in autonomous driving. Then the second perspective is socio-technical perspective, such that design, development, and deployment of autonomous cars should be human-centered, such that when such cars are designed, developed, and deployed, they should reflect the end users or stakeholders need. Also, they should kind of take people's prior opinions and expectations into account. So this is kind of socio-technical approach for the design and development of autonomous vehicles. And finally, the third reason is kind of philosophical perspective. So explainable AI or XAI decisions can provide kind of descriptive information about causality or causal inference of real-time actions, such that people are mainly interested, for example, why such kind of actions were chosen. So this brings kind of causality perspective as well. In addition to this, European Union has a specific regulation called General Data Protection Regulation. Probably you are already aware of this. And this regulation kind of necessitates the right of an explanation for end users, such that AI systems should provide some form of intelligent information to consumers about the behavior of the system. So this kind of GDPR regulation is kind of strictly enforced, and it's expected that almost all autonomous systems will have to kind of provide some forms of explanations to stakeholders and consumers. So if we summarize explainable AI for autonomous driving, we can say that these approaches are kind of AI-driven approach, which ensure kind of acceptable level of safety for a safe driving cars real-time decisions. Then explainable AI approach can provide explanations and transparency on a safe driving cars real-time decisions, particularly in kind of critical traffic circumstances. And finally, such kind of approach should obey all traffic rules which has been established by jurisdictions and regulators. So now that we understand the reason for explainable AI for autonomous driving, now let us go deeper with kind of concrete algorithmic approach. So supervised learning methods usually are not very effective in autonomous driving, except environmental perception, such that we use kind of convolutional neural networks and their augmented versions for scene understanding. And decisions are temporal and sequential, so they are made in real time. So it means that we have a sequential decision-making problem. We need reinforcement learning. So here I have drawn a kind of general graphics of reinforcement learning kind of setting for autonomous driving. So we have an agent, which is an autonomous car here. Since this agent in his kind of state performs actions like kind of steering and the braking or accelerating. And this is driving scene, which is its kind of operational environment. And by this way, an autonomous car kind of executes actions with highest reward kind of principle. So this is a general picture of reinforcement learning for autonomous driving. So given that we necessitate sequential decision making and explainability, it means that we need to develop explainable reinforcement learning methods for autonomous driving. Or explainable reinforcement learning also is known as XRL methods. Okay, now that we understand that we need explainable RL, but how can we develop explainable RL for autonomous vehicles? So based on my literature survey and kind of propositions, I found that there are at least 3 kind of potential approaches that we can leverage for explainable reinforcement learning. First of all, using textual explanations. We can describe an agent's decision linguistically using natural language processing method. For example, here there is a picture taken from Kim et al.'s paper published in ECCV. The car here provides kind of textual explanations in an intelligible format for end users. For example, if you look at here, it says the car is driving forward because there are no other cars in its lane. So here we can see that action is accompanied by a relevant explanation. So the car is driving forward, this is action, and because there are no other cars in its lane, this is relevant justification on this action. So this is just one simple form of kind of textual explanation on a self-driving car's decision. Then the second method is to provide visual explanations. For example, we can provide saliency maps, also known as heat maps, which kind of shows which part of the image, perceived image, is more important, more crucial for an agent's decision making. So, for example, another example have been provided here. You can see that based on this input image, an autonomous car kind of identifies which part of the perceived kind of image segment plays more role for its real-time decision making. So this kind of approach is also known as kind of saliency maps or heat maps. And finally, the third method could be Polishlevel explanations. For example, we can focus on developing interpretable reinforcement learning policies, such as by summarizing transitions. And by this way, kind of by summarizing transitions, maybe we can get some hint on developing interpretable reinforcement learning policies, which can eventually say why an autonomous car makes kind of specific action in a kind of specific time step.
Hello, one question.
Sure.
Yeah. So in the first approach, the textual explanation, it may be more about causal inference, because as you can say here, maybe the Kane's paper is saying the car is driving forward because there are no other car in its line. I think maybe it's more about the causal inference, and maybe we can use causal inference for the explainable reinforcement learning. Do you know any other work about explainable reinforcement learning by using causal inference?
Well, yeah, this is just kind of one form of causal inference because it provides causality on actions, right? So, well, there are kind of several approaches which kind of how to say. I have read several papers which shows that, which kind of gives examples like this action has been chosen because of this. Either it can be in the form of kind of just descriptive information or visual question answering. So visual question answering, I will talk about this later, but yeah, this is kind of one example of a causal kind of inference, but it has been provided in an intelligible format, in a natural language. So yeah, this is kind of causal inference, as you said, Ishan.
Yeah, okay, thanks.
Yeah, you're welcome. Thank you very much for pointing this. Yeah, so yeah, this is the third one. I mean, post-level explanations, as we discussed it, and the developing, in this case, we kind of focus on developing interpretable RL policies, such as by summarizing transitions. So 3 potential approaches which we can leverage for developing interpretable or explainable reinforcement learning for autonomous driving. So, and now that we understand kind of motivation for explainable AI and the reinforcement learning and how to generate one, there is another kind of big question. How can kind of explainable AI provide an opportunity to improve driving system safety, in addition to providing transparency in real-time or temporal decisions? Because autonomous driving is a safety critical application of artificial intelligence. That's why we also kind of propose that these explanations should somehow provide an opportunity to improve or enhance kind of safety of intelligent driving systems. But how? We answer these questions with concrete 3 case studies. First of all, having explanations can be helpful for real-time safety monitoring and control. So here I have shown one graphics from Schneider et al.'s kind of paper, which was published in intelligent user interface conferences. So what they have done is, in their autonomous driving study, they have provided an kind of user interface inside a vehicle, and they provide some forms of explanations to users inside the vehicle. This can be maybe backup drivers or passengers inside the vehicles. So three kinds of explanations have been provided here. First one is reactive critical, right? So it is a visual explanations, and using this kind of red science, it provides information that there is a kind of approaching danger ahead. So this is kind of critical traffic circumstances, right? Then the second one, in the middle, there is kind of proactive, non-critical traffic situation where kind of visual explanation has been provided in the user interface. It just gives information about the current traffic stations to end kind of users. And finally, in the third figure, you see that there is a textual explanation at the right. It's a kind of proactive, non-critical situation. So by leveraging textual and the visual explanations, a passenger inside the vehicle or backup driver can understand kind of traffic scene better, and they can also be alerted about the kind of possible danger. And another opportunity is that if autonomous cars are supplied with kind of control button, those passengers and backup drivers can kind of press that stop button, and they maybe can press that stop button, and they maybe can stop an autonomous car at the station and prevent any kind of accident in this case. So we can infer that such explanations can instill driving safety for passengers and any person inside the vehicle, and make the safe driving system more reliable and trustworthy. So we see that real-time explanations kind of have opportunity for real-time safety monitoring and control by this case study. Then the second example, one of the most famous example in autonomous driving, which is formulated as Molly problem. So what's the Molly problem? So Molly problem is given as follows. A young girl called Molly is crossing the road alone and is hit by an unoccupied self-driving vehicles. And there are no eyewitnesses in this situation. What should happen next? So this is a kind of difficult situation, right? So assume that you are an accident inspector and you would like to understand what happened in this kind of traffic scenario. Was the mistake by Molly, who kind of jaywalked in the kind of traffic, or was there kind of bad mistake made by an autonomous car? So how can explanations be helpful in this case from safety perspective? For example, there are two cases that explanations can provide kind of safety implications for this scenario. For example, a history of explanatory information on temporal actions of an autonomous car can give a clue regarding why an autonomous car continued to drive on in this kind of circumstance and eventually hit kind of Molly. And based on kind of these explanations, the driving system can be debugged and improved. So let us say based on the explanations of an autonomous car, we see that it was a mistake made by self-driving car. And this also provides an opportunity to debug and enhance the existing kind of intelligent driving systems. So here is another kind of safety gain with explanation. And the third famous test is Mcafe team's test on fooling Tesla's ADAS. So Mcafe researchers performed an intentional test to fool and test Tesla's ADAS system. So what they did is, in a kind of specific traffic road segment, they changed the speed limit sign. So they have extended the middle of 3 by a black tape. So you can probably see it from here. So this is not kind of ordinary 3, and they have extended the middle of 3 by a tape, and they wanted to see whether the Tesla's kind of heads-up display will read it correctly as 35 or will read it differently. And what happened is that they were really able to fool these other systems, and eventually a car understood this as 85 km/h and accelerated. So you see, this can cause kind of problem, right? So instead of maximum speed limit of 35, a car kind of understands this limit as 85 km/h and continues to accelerate. So what could be the role of safety in this case? So let us say if the car provides a relevant explanation, such as speed limit is 85, that's why I'm accelerating. It can be in post hoc or real-time manner. Then based on this explanation, we can understand that, okay, the car kind of got that speed sign as 85. It means that there is a problem with its kind of object detection or kind of, let us say, speed sign detection. So by this way, we can understand that it's kind of detection system, I mean, at least speed detection system is not fully safe, then it can be kind of debugged and enhanced. So again, with this example, we see that the explanations are essentials for autonomous driving. For autonomous driving, particularly for critical traffic circumstances. So in my current doctoral research, I am investigating several topics from the perspective of explainability. So first one is comparative study between model-free reinforcement learning and model-based reinforcement learning. So model-free reinforcement learning inherently lacks explainability of learning. Why? Because it's just based on taking action and collecting reward, and no any prior information is given initially. On the other hand, model-based reinforcement learning has a planning component, which can be explainable. So if you look at this diagram, we see that the agent takes an action, collects reward based on its policy. This is model-free RL. But in model-based RL, we have some kind of prior knowledge, which is kind of planning, right? And this planning can be explainable. So it means that model-based reinforcement learning has more potential than model-free reinforcement learning in terms of explainability. So this is one topic that I am currently investigating. This second topic to investigate is safety explainability dilemma, such that does explainability affect the kind of safety performance of an RL algorithm negatively? If you have ever done explainability research, you see that some people claim that when model becomes more explainable, its kind of performance in terms of, let us say, accuracy or safety drops. So we are also investigating this kind of dilemma, such that where the kind of improved explainability causes less performance by an RL algorithm. So in this context, what I am currently doing is I am trying to implement some model-free approach, such as DDPG, PPO, and SAC. Then I am also planning to implement model-based reinforcement learning approach, such as DINA, and then I will make a comparative analysis between these algorithms to see which one actually drives kind of a self-driving car more safely. So based on this comparative study, I would like to see their kind of performance from the safety perspective. And once we have kind of safest decision-making algorithm for the car, I am planning to develop explanations on top of them by using visual techniques, natural language processing methods in a linguistic format, and using interpretable policies, which we discussed previously. And I would like to give some information about my ongoing work. So regarding explainability part. So how in this context, I am kind of trying to use visual question answering. So visual question answering has not been kind of investigated within the setting of autonomous driving. However, it has a kind of great potential to provide explanatory information in autonomous driving decision making. But how? Well, there are kind of at least three kinds of VQA questions that we can use for explanatory purposes. The first one is kind of generating causal questions and answering. For example, if we look at this traffic segment, VQA system can generate such kind of question. Why was the lane changed to the right? And then it can provide answer using because the current lane narrows down ahead, right? So based on this kind of traffic segment, an autonomous car perceives the environment and its VQA system generates question and answering. So it's kind of justification on the selected action. So this is called visual causal question answering. And the second kind of explanation type could be descriptive questions, such as, for example, how many cars are around? The system can provide answer by 2, right? Kind of simple. And the third one would be kind of generating temporal questions. For example, what was the speed of the autonomous car before the emergency brake? And the answer can be provided as, let's say, 50 km/h. So we see that actually VQA can provide explanatory information or justification to judge kind of appropriateness of selected actions. So in my research, this is kind of current progress. I have presented my preliminary findings in AAA conference in Trustworthy workshop, and a longer version of this paper has been accepted for publication in the upcoming Explainable AI for Intelligent Transportation Systems book. And I have kind of a long journal paper, which is under review in Elsevier's Information Fusion Journal since last year, April. With that said, I recently worked on experimental part of my research. So what I have done is I implemented a deep deterministic pulse gradient algorithm, which can drive a self-driving car in the carless simulator. And eventually, with this implementation, an autonomous car was able to follow lane, go straight, turn left and right. And the Carla is an open source simulator which is actively used for autonomous driving research. So why I chose DDPG for this purpose? Because DDPG is of policy and the model for reinforcement learning, and it uses an actor-critic approach, which is kind of state-of-the-art reinforcement learning technique. And it has kind of 4 function approximators, which estimate policy and value functions, which are actor network, target actor network, critic network, and the target critic network. So actor network produces a specific action according to its current state. Then target actor network kind of yields the next action according to the next state. Then critic network critics the kind of these selected actions and calculates the state action value corresponding to the current state and action. And finally, target critic network kind of computes the state action value corresponding to the next state and action. So you see that one kind of estimates current state and action, the other one kind of calculates the next state and action. And the advantages of DDPG is that it is suitable for a continuous action space and it also leverages experience replay. Because autonomous driving task kind of consists of many discrete steps, we need kind of to have a kind of continuous action space where an agent can learn efficiently. In addition to this, DDPG uses experience replay. It means that once it kind of visited some kind of let us say states, it can reuse them in the later, and this is kind of a computational save some time for it. So how I represent state in with DDPG in this experiment? So I represent state in terms of an autonomous car speed, then a distance to center of the lane, which has been shown here, and the angle between the car and center of the lane. So here we have kind of a lane, we have waypoints, which is kind of drawn here, and the field of view, which shows how an autonomous car kind of views its kind of front view. So the ideal condition is that an autonomous car kind of moves in the middle of its current lane. And once it kind of deviates from its kind of middle of the lane, the reward will be kind of decreased according to the reward criteria, which I will explain next. So here our task is we use DDPG to drive a car from an initial point to the destination, where the route is generated by a star route planning algorithm. And expectation is that the car will stay in a lane, go straight, turn left and right as expected by this algorithm. And here is our kind of reward formulation, which I have adapted from Perez-Gil et al.'s paper published last year. So if collision happens, we of course give negative reward to the car. Then if a car is in its lane, then we give a reward to it based on this formula, which kind of considers angle of deviation from its kind of from the middle of the lane. And if the car kind of arrives its goal, we give a maximum reward of 100 for it. So this is our reward kind of shaping for DDPG on driving an autonomous car. And based on my preliminary empirical results, we have this learning curve and experimental demonstration. So you see that it kind of after some time step, the car's learning ability get kind of stable, and based on this experimental, how to say, insight, we can see that after some episode, an autonomous car is able to keep the car to stay in a lane and move ahead without kind of collision or without deviating from its lane. So I would like to show this one now for you. So this is kind of simulation environment. So you see the car kind of performs some high-level actions, such that in this case, it was able to turn right.
Have you tried other algorithms like PPO or TRPO in color by implementing it in the environment?
I haven't implemented TRPO or PPO so far, because I have just focused on DDPG, but in the future, I am planning to work on the implementation of those algorithms, because I would like to make a comparative analysis between DDPG, PPO, and the TRPO to see which one actually achieves highest kind of, let us say, safety score. But yeah, it's in my plan.
I remember there is a benchmark that includes not several algorithms in the benchmark, such as DDPG or SSA or PPO or TRPO or other sort of RA algorithms.
Benchmark, well, I have seen some implementation, but I haven't used that. I would be pleased if you maybe can provide a link of that benchmark.
Okay. Okay, maybe I can send an email to you later.
Oh yeah, thank you very much, Shantin. Yeah, that would definitely be helpful.
Yeah, no problem.
Yeah, thank you, Shantin. And yeah, this is just kind of some, let us say, experiments with this kind of car simulator. So uses that an autonomous car can stay in its lane and move forward without, for example, colliding with anything, without hitting the curb. And after some learning process, after some episodes, it can perform relevant actions appropriately. For example, you see here it was able to turn left as expected.
So in the video, do you consider the smooth trajectories, the smooth trajectory, because currently to shows like a genuine trajectory. So yeah. So how about the optimization about smooth trajectory?
Sorry, I couldn't get question, Shanding.
Yeah, I mean, so the trajectory we want to make sure that is smooth. Yeah, so the car can follow the trajectory. So how to figure out this problem in your experiments?
Yeah, here it's kind of waypoints. For example, this is the expectation. This is how to say waypoints which have been driven by route planner algorithm. So maybe I can.
So do you achieve this by design rewards?
Yeah, by rewards. Yeah. So based on that reward formulation, for example, I say that, okay, if it hits the curb, then the reward decreases and episode ends. But if it continues, let us say, straightly without, let us say, deviating from the lane, it gets positive reward. And this is kind of, waypoints, for example, if you look at here, this is a waypoint that car should follow. So this is waypoint, and this is an action taken by an autonomous car. For example, after some time step, we will reach kind of left turn, and it should be here. So waypoint should go this way. We will see it. So here we are. Yeah. So you see, it bent to the left, right, and autonomous car also kind of chose left action.
Okay.
So
Thanks.
Yeah, you are welcome, Shanting. And yeah, these are just kind of some experimental demonstration from preliminary empirical results. And you see that an autonomous car was able to, again, move forward, stay in its lane, turn left and right safely. And yeah, my next step is to apply video question answering mechanism to generate kind of explanatory description from that pre-trained log file. So I have kind of recorded that video file. Then I will use this kind of that pre-recorded file for generating causal, temporal, and descriptive questions. This is kind of ongoing phase of my research, which I hope to complete soon and get initial, let us say, explanatory system on the driving file. So if we can conclude the presentation, I would like to restate that I aim to develop explainable reinforcement learning approach for safe and interpretable autonomous driving. And explaining RL decisions can help us to understand the safety of autonomous cars' temporal decisions. And by this way, it can also provide an opportunity to debug the overall system. And in our proposed approach, reinforcement learning is kind of combined with computer vision and NLP methods to explain real-time decisions. And with kind of safe and transparent AI, we can move kind of to a step closer to, let us say, publicly approved and socially acceptable autonomous vehicles in the future. So this is the end of my talk. Thank you very much for your attention.
Okay, so a question. So do we have an official definition about explainable reinforcement learning? For example, what kind of reinforcement learning is explainable?
So yeah, that's a good question, Shanding. So actually, you know, reinforcement learning itself is kind of relatively new field. So when we do literature search on Google Scholar, we see that even the first papers on explainable reinforcement learning were published in 2019, just 3 years ago when I started my doctoral research. That's why, you know, this is still kind of evolving research topic. People still try to kind of give the definition of explainable RL, but at the highest level, we can say that, I mean, explainable RL means that we explain real-time decisions or action of an agent, autonomous agent. So this could be one kind of official kind of definition, but people still use kind of their own definition, but which is again close to what I said. The high-level goal is to interpret actions taken by autonomous agent.
Okay, I see. So it's a new error. So there's not something we can do in this error. Yeah. So any question, guys?
Okay, we have some questions from the audience now. So Yazin, yeah, you can like unmute and feel free to ask. Yeah.
Hi, can you hear me?
Yeah, I
Yes.
can hear you. Yeah.
Yeah, nice. Yeah, thank you, Shaheen, for your very nice topic and presentation. I actually had a question regarding the slide 16. I don't know if you can go back.
Sure.
Regarding the Molly question, Molly problem. Yeah, I had a scenario in my head that, let's say, the car hits the girl because the car fails to detect her at the first place. So, which means that our perception system fails to detect pedestrian properly, and also because I am working perception, so I know that there are also some explainable AI, especially based on like vision systems. And what I understood from your presentation and your work is mostly it's for the planner, like what are the sources of the decisions that the planner made. For example, if there is a car ahead, so the planner decides to go left or right to not keep the lane and so on. Do you think if there is also proper explainable AI used for the perception, which is not usually temporal and it's only by like single frame based, do you see an opportunity to also integrate that with those basically results that you can get from your perception, basically signals that you provide besides your final decision? Let's say if the pedestrian is not detected, maybe like it can be due to like environmental reasons or low lighting and so on. And it's basically one level even further, like to kind of integrate all together. Do you think it's challenging, and how challenging would that be?
Well, yeah, actually, thank you very much. That's a really great question, Yasin. You know, actually, autonomous driving is a really hard task. You know, there are so many factors contributing to overall safety of the intelligent driving system. For example, let us say fog weather, or let us say other muddy rain, other adverse atmospheric conditions can kind of deteriorate vision ability of an autonomous car. So what we can do is, I guess, providing just temporal explanations, real-time explanations for each action is the best choice to judge, how to say, vision ability of an autonomous car. For example, in my research, I particularly focus on generating real-time explanations. So why real-time explanations? As we said, real-time explanations can help us to control, how to say, to control or safety, to control and monitor safety of an autonomous car instantaneously, such that, let us say, we have a backup driver, and we have a we have a passenger inside the autonomous car, and the autonomous car is also supplied with potential alert button, let us say stop button, and gives a right to passenger to kind of press that button in case of unexpected scenarios. So regarding what are some kind of real-time explanations method, I guess what I have provided here, they are all kind of real-time explanations method, such that we, rather than focusing on specifically in post-hoc explanations, we just kind of or we just use, let us say, environmental perception, let us say video camera information, and then autonomous car maps this video camera information for its decisions, but at the same time it should generate kind of relevant explanations for an, let us say, end user or passenger. Let us say this heat maps method, heat maps or salience maps method. This is just one example of generating explanations in real time from vision, let us say, perspective. So if I go to this, this case, you see this is kind of real-time explanation method. So this is an environmental, let us say, scene in a traffic scene. This is a traffic scene which autonomous car observes, and here is kind of, it's, let us say, a real-time visualization method. For example, you see that autonomous car highlights this object, this object, this object, this object, and this object. 5 objects as the most crucial ones, which kind of affect its decision making. So if I understood your question correctly, so you are mainly focusing on what are the explainable vision methods, mainly explainable vision methods for autonomous car, then I would say using saliency maps or heat maps would be a good choice to understand, for example, why an autonomous car, let's say, proceeds ahead with its current actions. So does that answer?
So maybe, yeah, basically I'm a little bit familiar with saliency and also this approach. And also there are also some that not only focus on the only like one saliency map, they also look at intermediate layers like the convolutional layers to see like if there is any problem there. My question is more regarding if, okay, let's say in real time, the heat map basically provides no heat region around one pedestrian, and is there any way to kind of interpret this or translate this to a failure, like to kind of predict that our perception is failing to detect a pedestrian and then generate the warning signal that you said based upon, let's say, yeah, we don't see the pedestrian, hard brake, or even because there is like a problem that I am actually also trying to solve, like if you don't see the pedestrian, then you don't see it, right? So how do you know that you don't see the pedestrian? So that's like a concern, how the system knows that it doesn't see the pedestrian, and if there is a heat map even providing slightest information that there might be a chance that the pedestrian is overseen, then I think it will be very very nice to have. But yeah, I mean, I don't want to talk too much, but really nice to see also your work. If you have also any comment on that, we'll be very happy to hear that.
Yeah, actually, that's a really great question, Yasin. Yeah, I really like it. But yeah, it's really, difficult regarding, for example, if, let us say, pedestrian is missed from, let us say, perception system of an autonomous car, and let us say that heat maps also fail to detect that pedestrian. How we can understand that there's a problem? Yeah, that's a kind of difficult question. I mean, probably we should research more about this, but probably it means that there is a problem with perception system. But in which components there is a problem, I guess this more goes to kind of computer vision perspective. So I'm not fully, let us say, I am not one is fully expert in vision-based autonomous driving. Rather, I mainly focus on, let us say, reinforcement learning. But probably we should look at the literature regarding where, if, let us say, some important objects are missed from perception system of an autonomous car, then how can we kind of detect it? This is a good question.
Definitely.
Probably. Yeah, this is probably,
exactly.
yeah,
Like
I should also take a look at it.
Yeah, I mean, one thing that I like about your approach is to consider like or integrate all the temporal information, from the system, and maybe like let's say we usually train our perception DNNs on some very limited training data sets, right? So if you can derive conclusions that, for example, if the heat map kind of degrades from a level, then there might be a chance of failure. And if you can kind of integrate this information in real time in your RL-based approach, then you say like in the last, I don't know, 15 frames or 15 time steps, like 5 or 10 of them are having degrading heat maps, then there might be, I mean, I'm just thinking loud, there might be a chance that you can predict that the network gonna fail or is failing right now. The perception network, precisely. I mean, there could be a really good potential to kind of integrate that, but it needs also a lot of analysis on the perception DNN to see why and how does it fail, and do you see those failures in terms of patterns whatsoever from the explainers like the saliency maps. But really nice topic. Yeah, thank you.
Yeah, you're welcome, Yasin. That's a great question as well. Yeah, I mean, it's really interesting. So autonomous driving is a hard task, really.
Of course, yeah. Especially the safety of it is like.
Exactly, yeah.
Okay, do we have some other questions from the audience?
Yeah, I would have a question. So first of all, thanks very much for the talk. It was very interesting. My question would be about the text-based explainable RL. And I was just wondering if you could give an intuition about like what the objective function is that you're training for. Is this like a supervised problem? So are you maybe using a transformer and then with the action tokens that are chosen, trying to put out the text, or how is this working?
So yeah, that's a great question. Thank you very much, Daniel, as well. So yeah, we use kind of transformers for, I mean, there are several methods that we can generate text, textual description on an autonomous car, but transformers are kind of one step ahead to use. So I see that based on my current literature search, I have seen that people mainly use transformers, such as BERT, let us say. They use BERT. But what they, how they actually is like this. They first take some training data, let us say a traffic segment, right? Then they use human annotation to generate explanations for that action. Let us say they take this action and they annotate these decisions based on traffic scene, like let us say, or the car is driving forward because there are no other cars in its lane. So they eventually develop some kind of vocabulary with this annotation system, and then for this testing data, system then eventually becomes able to generate relevant explanations. But firstly, yeah, it needs human annotation, such that okay, this is action, this is kind of traffic scene, this is a selected action, and this is a relevant explanation, which has been provided by human annotation. So after system learns such kind of annotation, it can eventually generate, let us say, further textual descriptions using these transformers like BERT.
Okay, thank you very much.
Yeah, you are
and
welcome.
what is your intuition then? Because of course you're only training on trying to explain what is happening, but not really why decisions are made, right? So you don't know. If you're in reinforcement learning and your car is making decisions, you don't get really an explanation of why the decisions were taken, only, I guess, an explanation of what is happening, right?
Mm-hmm. Yeah, that's a good question as well. So, you know, let us say these explanations may not sometimes reflect the real-time action taken by an agent. Let us say agent takes this action, let us say action A, but we see that eventually system produces an explanation which does not correspond to that action. That's why, I mean, those, let us say, explanations which have been generated in the testing phase should be evaluated using human judgment. So, but because, let us say, by generating direct explanations from an RL agent's action, it's a very difficult task. That's why we should somehow, let us say, incorporate natural language-based methods. Let us say transformers like BERT to describe its actions. Otherwise, because you know, interpreting RL agents' action is difficult, because currently I haven't seen, I mean, works that can directly kind of generate intelligible explanations based on rewards. Because we need to deliver explanations in an intelligible format, which can be understood by people. So the best approach in this context is we just use some kind of human annotation for, let us say, several traffic images, several traffic scene, and then once our system becomes sophisticated enough, then for the unseen, let us say, test scenes, RL agents decisions, which RL agent which drives a car, this then explanatory information can be provided by these natural language-based explanations. So did it answer to your question, Daniel? Or
yeah, thank you. I'm just thinking that I guess the system will only learn to explain things as much as any human could explain the actions of the agent in the end, right? So
yeah, that's true. Because it's really hard task. I mean, generating explanations are not usually easy task. There should be human involvement, right? Because once humans are, let us say, humans are experts in providing natural language-based descriptions. Once we provide such kind of descriptions, once we feed it to our model, then by by means of state-of-the-art, let us say, transformers like BERT, we can generate, we can actually achieve kind of good explanations that reflect an RL agent's decisions in testing phase as well.
Okay, thanks very much.
Yeah, thanks, Daniel, as well.
If anybody has questions, I would have some.
Yeah, maybe to add a little bit on this, just like because you mentioned generating human annotators to help generating the text. So there is a one step ahead option which they're using now. It's as I understand in ChatGPT. So the idea is basically to let the model generate text, because it's very time consuming for humans to generate the text, but then the humans do the ranking. So the model generates several sentences, and the human just annotates 1 to 10 how good that sentence is describing the situation. And this is easier to generate for humans than writing the sentences. And this is how they actually achieve very good results on the chat model itself, because now you need much less time to generate text, but you also have the human help there to understand what is good and bad. So this, I think, can be applied in this situation also.
Yeah, I guess, ChatGPT is also becoming famous. This could also be applied. And I would also like to give you some paper about this. So I will show you one paper which was published in CVPR 2021. It's called Next QA Framework, Next Phase of Question Answering to Explaining Temporal Actions. So this framework actually was able to generate temporal explanations for temporal actions. For example, if you look at this scene, this Next-K framework provides explanation. Why was a toddler in red crying at the end of the video? And the explanation is that it fell backwards. And the second, let us say, descriptive explanation is, how did the lady help the toddler who fell at the end? And explanation becomes, pick the toddler up. So this is kind of one of the recent and the powerful, let us say, frameworks that can explain temporal actions. As you said, I mean, we can leverage maybe ChatGPT for these purposes, but what they have done is they have also used kind of human annotation. So if you look at here, they say that annotation of the Next-K dataset was done in 3 stages over 1 year by 100 undergraduate students. So we see that humans are kind of, again, important for generating kind of good explanations in autonomous systems. I mean, there should be human involvement, such that it should be human-centered or human-in-the-loop autonomous driving. This is kind of my approach to this.
Yeah, thank you. Other questions from the audience?
I would have one more if nobody else has a question. So my use case, and I'm working in the reinforcement learning for infrastructure maintenance and inspection. And I'm also, for my project, it's not relevant right now, but it will be. I'm still at the beginning. And one of the things that I think will happen is that we are using reinforcement learning agents to solve these kinds of tasks, of course. But there is not really a human expert to judge, to see all these maintenance trajectories and then provide any explanations, right, as to why this specific maintenance was done at this point. So is there any approach you could think of that maybe goes in this direction?
So yeah, I think the best approach would be to again use ground truth, such that, for example, maybe you can employ some humans. You can ask them, for example, in your point of view, what is the relevant annotation or explanation for your task, let us say. Once you have, let us say, ground truth, let us say, explanatory information, and then you can kind of use AI to generate explanations like I showed there. Then you can see how your generated explanations match those ground truths. And there is also kind of score called WHOOPS score. I will write it in here, WHOOPS score. So WHOOPS score shows how the system generated explanations are close to their ground truth, or let us say perfect explanations. So I would say, again, using human annotation would be a better choice, such that you can use human judgment to get ground truth explanations, and then you can use your own model to generate explanation and compare how your system's explanations are close to that ground truth. I guess this is a kind of common way that current AI literature does in terms of explainable AI research. Maybe you could use it for your purpose as well.
Okay, thanks.
Yeah, you're welcome.
Okay, thank you. Any other questions? Okay, there are no more questions from the audience. So thank you very much for this very nice talk. It was a pleasure to have you in our reading group at the Technical University of Munich. So again, thanks for Shangling also for the initiative and hosting. And yeah, we'll be happy to hear news from you when you have something else published. And yeah, feel free to let us know, and looking forward to any news on that side.
Yeah, thank you very much, Joseph, and thank you very much, Shangting, and thank you very much all for your time today to participate in today's meeting. Questions are really great. I believe they are helpful to improve my research as well, and I will definitely be happy to kind of share, hopefully, further kind of publications out of this research with you. Hopefully, we will have kind of better research with such kind of collaboration. Thank you very much for your time.
Thank you too. And then we'll be, yeah, Shangling.
Okay, thank you, Yusuf, and thank you for Shaheen's great talk. Yeah, and,
yeah, thanks, Shangling.
Yeah, thank you. And then we'll be in contact regarding the recording, and if we'll message you after the meeting in the next days to summarize that. Thank you very much.
Yeah, thanks, Joseph. Yeah.
Thank you all for joining, and until the next meeting, have a good time. Thank you. Bye-bye.
Thank you. Bye-bye.
Thanks, guys. Bye-bye.
Thank you all.
Bye.
Thank you.